In 1937, the physicist Paul Dirac was thinking about the universe. He was a quiet man, known for his precision, but he did not waste words. He worked with numbers, and some numbers were bothering him. He looked at two completely different parts of physics. One was the universe itself. The other was the tiny world of atoms. He calculated a ratio. He took the age of the universe, which was then estimated to be about 2 billion years. He divided it by the time it takes light to cross a proton. A proton is incredibly small. The time is incredibly short. The result was a huge number, a number with about 40 zeros after it, 10 to the power of 40. Then he calculated a second ratio. He took the strength of the electrical force between a proton and an electron. This is the force that holds atoms together. He divided it by the strength of the gravitational force between them. Gravity is very weak at this scale. The electrical force is much, much stronger. The result was another huge number. A number with about 40 zeros after it, 10 to the power of 40, the numbers were the same. This was strange. One number came from cosmology, the size and age of everything. The other number came from particle physics, the forces inside a single atom. There was no known reason in physics why they should be related at all. It was an eerie coincidence. Dirac did not believe in coincidences like this. He thought it meant something profound. He suggested that maybe the fundamental constants of nature were not constant. Maybe the force of gravity was getting weaker as the universe got older. This would keep the two numbers in balance. His idea was called the large numbers hypothesis. Experiments later showed that the force of gravity is very stable. It does not seem to be changing. So Dirac's specific solution was probably wrong, but the problem he found did not go away. We just happen to live in the exact moment in cosmic history when the age of the universe, measured in atomic time, matches the force ratio of the universe's most common particles. The coincidence remains. It is one of many numbers that seem just right. Too right. And they make scientists question everything. Number 17, Dirac's large numbers are not supposed to exist. The mass of the observable universe is about 10 to the power of 53 kilograms. This is roughly 10 to the power of 80 protons and neutrons. The number 10 to the power of 80 is the square of 10 to the power of 40. The radius of the observable universe is 13.8 billion light years, which is also a number related to 10 to the power of 40 when measured in atomic units. Let's break down the coincidence Paul Dirac found in 1937. It is more than just two numbers. It is a family of very large, similar numbers that connect the very big with the very small. There is no theory that explains why this should be true. It is just an observation. First, consider the number 10 raised to the power of 40. It is a 1 followed by 40 zeros. It is hard to grasp how big this is. The number of grains of sand on all the beaches on Earth is about 10 raised to the power of 20. The number of stars in our galaxy is about 10 raised to the power of 11. The number of galaxies in the observable universe is about 10 raised to the power of 12. So 10 raised to the power of 40 is a number beyond any normal experience. Dirac's first ratio was about time. He compared the age of the universe t with a tiny unit of time derived from atomic physics tonnery. Let's use more modern values. The universe is about 13.8 billion years old. That is 4.35x 10 raised to the power of 17 seconds. The atomic unit of time can be the time it takes light to travel the classical electron radius. This is about 10 raised to the power of 23 seconds. If you divide the age of the universe in seconds by this tiny unit of time, you get a number around 10 raised to the power of 40. This ratio is not constant. The universe is getting older, so this number is getting bigger. When the universe was half its current age, this number was half its current value. Dirac's second ratio was about forces. The electromagnetic force holds electrons in orbit around the nucleus of an atom. The gravitational force also pulls the electron and proton together, but it is much weaker. To find the ratio, you use the formulas for each force. Many of the terms, like the distance between the particles, cancel out. You are left with a ratio of fundamental constants: the charge of the electron, the speed of light, the gravitational constant, the mass of the electron, and the mass of the proton. When you put all these numbers in, you get another value around 10 raised to the power of 40. This second ratio, unlike the first, should be constant. All the values in it are considered fundamental constants of nature. They are not supposed to change over time. So here is the problem. One ratio is changing over time, the other is constant, but right now, today, they are the same. This implies we are living in a special time, a special epoch in the universe's history. Dirac found this too unlikely. He proposed a radical solution. He said maybe the constants are not constant. He suggested that the gravitational constant g is actually decreasing over time. As the universe gets older and t increases, g decreases to keep the force ratio in lockstep with the time ratio. This would mean that gravity was much stronger in the early universe. This was a testable idea. Astronomers and physicists got to work. They looked for evidence of a changing g. If gravity were stronger in the past, the orbits of planets and moons would have been different. The moon, for example, is slowly moving away from the Earth. By using lasers to bounce light off reflectors left on the moon by Apollo astronauts, scientists can measure this distance with incredible precision. The measurements show the moon's retreat matches the predictions of standard gravity. There is no room for a changing g of the magnitude Dirac required. They also looked at distant stars and galaxies. The light from them tells us about the physics of the past. The way stars burn, the light they emit, and how they explode as supernovae all depend on the value of G observations of distant supernovae, and the cosmic microwave background radiation have put very tight limits on how much G could have changed. The consensus is that it is constant. So Dirac's elegant solution is gone. We are back to the original puzzle. Two giant, unrelated numbers just happen to match up during the time humans are around to notice. There are other large numbers that join the family. The total number of particles in the universe, mostly protons and neutrons, is estimated to be around 10 raised to the power of 80. That is 10 raised to the power of 40, raised to the power of 2. This is called the Eddington number, after Sir Arthur Eddington, who first noted its strangeness. Why should the total number of particles in the universe be the square of the other two ratios? There are a few possible explanations, none of them completely satisfying. One is that it is a complete fluke. In a universe of countless numbers and relationships, some will appear to match up by pure chance. Most scientists find this explanation hard to accept, given the scale of the numbers. Coincidences involving small numbers are common. Coincidences involving numbers with 40 zeros are not. Another idea is the anthropic principle. This principle suggests that the universe must have properties that allow intelligent life to exist and observe it. If the physical constants were different, we would not be here. Perhaps there is some undiscovered link between the age of the universe and the force constants that is necessary for the formation of stars, planets, and life. And for life like ours to evolve, the universe needs to be a certain age. It needs to be old enough for stars to have formed, lived, and died, creating the heavier elements like carbon that are essential for life. It cannot be too old, or all the stars would have burned out. So we find ourselves in this specific epoch. Maybe the matching of the large numbers is a side effect of this requirement. A third possibility is that our understanding of physics is incomplete. There might be a deeper theory, a theory of everything that connects cosmology and particle physics in a way we do not yet understand. In this future theory, the relationship between these numbers would not be a coincidence at all. It would be a necessary consequence of the laws of nature, but we do not have that theory yet. So, for now, we are left with Dirac's Eerie numbers, a cosmic coincidence of 1 in 10 raised to the power of 40. A hint that there is something fundamental about the universe we have not yet grasped. Number 16, the moon, exactly covers the sun. The sun is 1.39 million kilometers in diameter. The moon is just 3,474 kilometers in diameter. The sun's diameter is almost exactly 400 times the moon's. The sun is, on average, 149.6 million kilometers from Earth. The moon is, on average, 384,400 kilometers from Earth. The sun is about 390 times farther away. These two ratios are so close that from the surface of the Earth, the sun and the moon appear to be the same size in the sky. This precise alignment allows for the spectacle of a total solar eclipse. When the moon passes directly between the Earth and the sun, it blocks the sun's bright face, the photosphere. This reveals the sun's much fainter outer atmosphere, the corona. The corona is a wispy, ethereal halo of plasma that stretches millions of kilometers into space. It is only during a total solar eclipse that we can see it from Earth with the naked eye. This is not a normal arrangement. No other planet in our solar system has a moon that does this. Mars has two tiny moons, Phobos and Deimos. They are too small to ever cover the sun. They look like little potatoes crossing the solar disk. Jupiter and Saturn have giant moons, but they orbit far from the planet or are large enough that they more than block out the sun. A total solar eclipse on Earth is a unique event in our solar system. The scientific value of this coincidence has been immense. Before the space age, eclipses were the only way to study the corona. In 1868, during an eclipse, French astronomer Pierre Janssen discovered a new spectral line in the corona's light. This line did not match any known element on Earth. British astronomer Norman Lockyer proposed it was a new element, naming it helium, after Helios, the Greek god of the sun. Helium was not discovered on Earth for another 27 years. Perhaps the most famous use of a solar eclipse was in 1919. Sir Arthur Eddington, a British physicist, led two expeditions, one to Brazil and one to the island of Principe off the coast of Africa. Their goal was to test Albert Einstein's new theory of general relativity. The theory predicted that gravity from a massive object like the sun should bend the path of light from distant stars. Normally, the sun's glare makes it impossible to see stars near it. But during a total eclipse, the sky darkens and those stars become visible. Eddington's team photographed the star field around the eclipsed sun. They compared the positions of the stars to photographs taken 6 months earlier when the sun was in a different part of the sky. The stars' positions had shifted. The amount of the shift matched Einstein's predictions almost exactly. It was a stunning confirmation of the theory and made Einstein a worldwide celebrity. The coincidence is even more fragile than it first appears. The moon's orbit is not a perfect circle. It is an ellipse. When the moon is at its farthest point from Earth apogee, it appears slightly smaller in the sky. If an eclipse happens, then it cannot completely cover the sun. This results in an annular eclipse, where a bright ring or annulus of the sun remains visible. When the moon is at its closest point perigee, it appears slightly larger and can easily produce a total eclipse. But there is a bigger, more permanent change happening. The moon is slowly moving away from the Earth. Tidal forces between the Earth and moon cause the Earth's rotation to slow down slightly, and this angular momentum is transferred to the moon, pushing it into a higher orbit. The rate of retreat is about 3.8 centimeters per year. This is about the speed your fingernails grow. It does not sound like much, but over geological time, it adds up. Billions of years ago, the moon was much closer to Earth. It would have appeared huge in the sky. Any solar eclipse would have been total, but it would have blocked not just the sun, but a large portion of the sky around it, hiding the corona. In the distant future, the moon will be so far away that it will never be large enough to completely cover the sun. All solar eclipses will be annular. Total solar eclipses are a temporary phenomenon in Earth's long history. Scientists estimate that they will cease to happen in about 600 million years. The fact that we live in the brief window of Earth's history when this perfect alignment occurs is remarkable. The window for perfect eclipses, where the moon just barely covers the sun to reveal the corona, is even narrower. So we have a situation where a planet has a single large moon. The moon is just the right size and at just the right distance to perfectly blot out the local star. This arrangement happens during a specific geological era when intelligent life has evolved and developed the tools of astronomy to observe it. This has allowed for fundamental discoveries about the universe, from the composition of stars to the nature of gravity itself. It is a chain of coincidences. Remove any one of them, and our scientific history would look very different. Number 15. The unreasonable flatness of space. The universe has a shape. On the largest scales, space-time can be curved. According to Einstein's general relativity, mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. There are three basic possibilities for the geometry of the universe. It can be closed, like the surface of a sphere. If you travel in a straight line in a closed universe, you will eventually end up back where you started. It can be open, like the surface of a saddle. In this case, parallel lines diverge. Or it can be flat, like a sheet of paper. In a flat universe, parallel lines stay parallel. The geometry you learned in school works. Which one is our universe? The answer depends on the total amount of mass and energy it contains. There is a specific value called the critical density. If the actual density of the universe is greater than the critical density, the universe is closed. The mutual gravity of all the matter will eventually halt the expansion and cause it to collapse in a big crunch. If the density is less than the critical density, the universe is open. Gravity is too weak to stop the expansion, and it will expand forever. If the density is exactly equal to the critical density, the universe is flat. It will also expand forever, but the expansion rate will slow down, approaching zero. This balance is incredibly delicate. The value of the density parameter, omega O, is the ratio of the actual density to the critical density. If O is greater than 1, the universe is closed. If O is less than 1, it is open. If O is exactly 1, the universe is flat. Here is the coincidence. All our measurements today, primarily from the cosmic microwave background radiation, show that the universe is extremely close to flat. The value of omega is 1, with a margin of error of only about 0.5%. This might not sound very impressive, but the problem is that a flat universe is an unstable state. It is like balancing a pencil on its point. Any tiny deviation from perfect flatness in the early universe would have been magnified enormously over 13.8 billion years of expansion. Let's go back to the very early universe, 1 second after the Big Bang. For the universe to be as flat as it is today, the density back then must have been tuned to the critical density to an astonishing degree of precision. The deviation from omega equals 1 could not have been more than 1 part in 10 raised to the power of 15. That is 0.000000000000001. A few seconds earlier, at the Planck time 10 raised to the power of 43 seconds after the Big Bang, the tuning had to be even more precise. The density had to be equal to the critical density to within 1 part in 10 raised to the power of 62. If the initial density had been just slightly higher by 1 part in 10 raised to the power of 60, the universe would have recollapsed into a singularity within a few million years, long before stars, galaxies, or life could have formed. If the initial density had been just slightly lower by the same amount, the universe would have expanded so rapidly that matter would have thinned out too quickly. Gravity would have been unable to pull material together to form galaxies and stars. The universe would be a cold, empty, and dark place. Like, this is the flatness problem. Why was the early universe so exquisitely balanced on this knife's edge between collapse and rapid expansion? Standard Big Bang theory offers no explanation. It simply assumes this initial condition as a given. It is a starting value that has to be put into the equations by hand to make the universe look the way it does today. To solve this, cosmologists in the 1980s, including Alan Guth, proposed the theory of cosmic inflation. Inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion. It grew exponentially, doubling in size at least 100 times in a sliver of a second. This rapid stretching would have taken any initial curvature the universe had and flattened it out. Think of the surface of a balloon. When it is small, its curvature is obvious. If you inflate that balloon to the size of the Earth, a small patch on its surface will look almost perfectly flat. Inflation does the same thing to the universe. It stretches the cosmos to such a colossal scale that our observable part of it appears flat regardless of its initial shape. Inflation is a powerful and elegant idea, and it solves the flatness problem. It also solves other cosmological puzzles, like the horizon problem. But inflation itself is not a proven fact. It is a theoretical framework, and while it fits the data well, we do not have direct proof that it happened. We also do not know what caused inflation or how it stopped. So we are left with a choice. Either the universe began with an initial density tuned to an accuracy of 1 part in 10 raised to the power of 62 by pure chance, or a process like inflation happened. And if inflation happened, it suggests that our observable universe might be just one tiny flat patch in a much larger, possibly infinite multiverse where other regions could have different properties and shapes. The flatness of our universe is either an incredible coincidence or a clue that we are part of something much, much bigger than we can see. Number 14, the cosmic microwave background's uniform temperature. In 1964, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for radio astronomy. Well, they were frustrated by a persistent, faint hiss of microwave noise. It came from every direction in the sky, day and night, season after season. They checked everything. They cleaned the antenna, removing what they described as a white dielectric material, which was pigeon droppings. The noise remained. At the same time, at nearby Princeton University, a team of physicists led by Robert Dick was building a detector to search for the very thing Penzias and Wilson had found. They were looking for the leftover heat from the Big Bang. The theory predicted that the early universe was incredibly hot and dense, filled with a glowing plasma. As the universe expanded and cooled, this light should have stretched out, redshifting into the microwave part of the spectrum. When the two groups learned of each other's work, it became clear what the hiss was. Penzias and Wilson had stumbled upon the cosmic microwave background CMB, the afterglow of creation. They won the Nobel Prize for their discovery in 1978. The CMB is a snapshot of the universe when it was only 380,000 years old. At that point, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This event is called recombination. Before this, the universe was an opaque fog of charged particles that constantly scattered light. After recombination, the universe became transparent and the light was free to travel through space unimpeded. The CMB is that light which has been traveling for 13.8 billion years to reach us. Here is the eerie part. When we measure the temperature of the CMB radiation, it is almost perfectly uniform in every direction we look. The temperature is 2.725 Kelvin, which is just a few degrees above absolute zero. The variations in temperature from one spot in the sky to another are tiny, only about 1 part in 100,000. It is one of the smoothest, most uniform things ever measured in nature. This uniformity is a massive puzzle. It is called the horizon problem. Look at 2 opposite points in the sky. The light from the CMB at one point has traveled 13.8 billion years to reach us. The light from the CMB at the opposite point has also traveled 13.8 billion years to reach us. The total distance between these 2 points is 27.6 billion light years, but the universe is only 13.8 billion years old. According to the theory of relativity, nothing, not even information, can travel faster than the speed of light. This means that these two opposite regions of the early universe could never have been in causal contact. They were too far apart for any heat or information to have traveled between them in the time available. So, why do they have the exact same temperature? It is like walking into a huge room and finding that the temperature in every corner is identical to 1,000th of a degree, but that the heating and cooling systems have never been turned on and the air has never circulated. There is no physical reason for them to have reached thermal equilibrium. The standard Big Bang model cannot explain this. It is another initial condition that has to be assumed. The theory of cosmic inflation, which was proposed to solve the flatness problem, also provides a solution here. Before the period of inflation, the entire region that would become our observable universe was a tiny subatomic patch. This patch was small enough to have been in causal contact and to have reached a uniform temperature. Then, inflation kicked in and stretched this tiny, smooth region to astronomical sizes. The uniformity was preserved. The regions that are now on opposite sides of our sky were once right next to each other. Inflation elegantly solves the horizon problem, but as with the flatness problem, it replaces one mystery with another. We do not know the mechanism behind inflation, and it leads to the idea of eternal inflation, where our universe is just one bubble in a sea of countless other bubble universes, each potentially with its own physical laws. So the smooth, uniform temperature of the afterglow of the Big Bang is not just a curiosity. It points to a deep problem with our standard model of the universe. It is either a coincidence of incomprehensible proportions where countless disconnected regions of the early universe all happen to start at the exact same temperature, or it is evidence of a dramatic, hyper-accelerated expansion in the first moments of time. The quiet hiss that Penzias and Wilson found is the echo of one of the deepest puzzles in cosmology. Number 13. The cosmological constant's tiny value. In 1917, Albert Einstein had just completed his theory of general relativity. When he applied his equations to the entire universe, he found something he did not like. They predicted that the universe must be either expanding or contracting. It could not be static. But at the time, the prevailing view among astronomers was that the universe was static, eternal, and unchanging. To fix this, Einstein added a new term to his equations. He called it the cosmological constant. It acted as a kind of anti-gravity, a repulsive force that would, push space apart and, balance the inward pull of gravity, allowing for a static universe. A decade later, in 1929, astronomer Edwin Hubble showed that the universe was not static at all. He observed that distant galaxies were all moving away from us, and the farther away they were, the faster they were moving. The universe was expanding. Einstein reportedly called the cosmological constant his biggest blunder. He threw it out of his equations, but the story was not over. In 1998, two independent teams of astronomers were studying distant supernova to measure the rate at which the universe's expansion was slowing down due to gravity. They found the exact opposite. The expansion was not slowing down, it was speeding up. The universe is accelerating. To explain this, physicists had to bring back Einstein's blunder. The cosmological constant, or something like it now called dark energy, appears to be real. It is a mysterious energy inherent in the fabric of space itself, pushing everything apart. Here is the coincidence, and it is considered by many physicists to be the single biggest problem in physics today. We can try to calculate the value of the cosmological constant from our understanding of quantum mechanics. In quantum field theory, empty space is not empty. It is a seething cauldron of virtual particles and energy fields popping in and out of existence. This is called the vacuum energy. This vacuum energy should have a gravitational effect. It should act exactly like a cosmological constant. When physicists calculate the theoretical value of this vacuum energy, they get a number that is absurdly large. It is 10 to the power of 120 times larger than the value we observe from astronomy. That is a 1 with 120 zeros after it. This discrepancy is the largest mismatch between theory and observation in the history of science. It is called the cosmological constant problem, or the vacuum catastrophe. To put this number in perspective, if the cosmological constant were as large as the theory predicts, the repulsive force of space would be so enormous that the universe would have been torn apart in the first fraction of a second. Atoms could not hold together. Stars and galaxies could never have formed. The universe would be an empty, expanding void. The observed value of the cosmological constant is incredibly, unnaturally small. It is not zero, but it is very close to it. The value is just large enough to cause the cosmic expansion to start accelerating a few billion years ago. The problem is that the vacuum energy from quantum physics and the energy from gravity seem to be canceling each other out with a precision of 120 decimal places, but not perfectly. There is a tiny non-zero leftover amount that we call dark energy. Why this incredible cancellation? There is no known principle in physics that would cause this. It is as if you had two colossal numbers, each with 121 digits, and you subtracted one from the other, and the answer was 7. It would not seem random. You would assume there is some deep reason for the near-perfect cancellation. There is another wrinkle to this coincidence. The density of matter in the universe decreases as the universe expands. But the density of dark energy, the cosmological constant, is thought to be constant. It does not dilute. This means that in the early universe, matter and radiation dominated, and the effect of dark energy was negligible. In the far future, dark energy will completely dominate and matter will be irrelevant. We happen to be living in the very specific epoch where the density of matter and the density of dark energy are of the same order of magnitude. This is called the coincidence problem. Why now? There are some proposed solutions. One is the anthropic principle. In a multiverse with many different universes, the cosmological constant might have a different value in each one. We would, of course, find ourselves in one of the very rare universes where the value is small enough to allow for the formation of galaxies, stars, and observers. In all the others, no one would be around to measure it. Another idea comes from string theory, which suggests a vast landscape of possible universes, perhaps 10 raised to the power of 500 of them, each with different physical constants. Our universe could be one where the constants just happen to be right, but these ideas are currently untestable. The tiny non-zero value of the cosmological constant is a profound mystery. It suggests that our existence depends on a cancellation of cosmic forces, so precise it defies explanation. It is a number that sits at the intersection of our two best theories of the universe, general relativity and quantum mechanics, and it tells us that we are missing something big. Number 12, Hoyle's carbon resonance. All the carbon in your body, the fundamental element for life as we know it, was forged in the heart of a star. But for a long time, physicists had a problem. They could not figure out how stars made it. The process of stellar nucleosynthesis, how stars create heavier elements from lighter ones, was a major puzzle in the 1940s and 50s. Stars, like our sun, get their energy by fusing hydrogen into helium. This is the first step. The next step is to fuse helium into heavier elements. The most straightforward way would be to fuse two helium-4 nuclei together. A helium-4 nucleus has 2 protons and 2 neutrons. Fusing 2 of them would create a nucleus with 4 protons and 4 neutrons. This is beryllium-8. The problem is that beryllium-8 is incredibly unstable. It has a half-life of about 10 raised to the power of 16 seconds. It falls apart almost instantly, breaking back down into 2 helium nuclei. So for a third helium nucleus to come along and fuse with the beryllium-8 to make a stable carbon-12 nucleus, it has to do so within this impossibly short time frame. The conditions inside a star are hot and dense, but not that dense. The odds of this happening were calculated to be far too low to account for the amount of carbon we see in the universe. The universe is full of carbon. We are made of it. It is clear that stars did solve this problem. In 1952, the astronomer Fred Hoyle was working on this puzzle. He reasoned that if the three-body collision was too rare, there must be a way to speed it up. He proposed that there must be a resonance in the carbon-12 nucleus. In nuclear physics, a resonance is an excited energy state. If the combined energy of the beryllium-8 and the incoming helium-4 nucleus exactly matched an excited energy level of carbon-12, the reaction would be dramatically enhanced. The nuclei would want to snap together into that state. It is like pushing a child on a swing. If you push at just the right frequency, the resonance frequency, a small push has a big effect. Based on the temperature inside stars where helium fusion occurs, Hoyle calculated that the carbon-12 nucleus must have a resonance state at a very specific energy, 7.65 mega-electron-volts MeV. He was a theoretical astronomer. He made this prediction without any experimental evidence. He was so confident that he went to a team of nuclear physicists at Caltech, led by William Fowler, and urged them to look for this state. The Caltech team was skeptical. Nuclear energy levels were not something you just predicted from astrophysics, but they ran the experiment. They bombarded a nitrogen-14 target with particles to create excited states of carbon-12, and they found it. A resonance state exactly where Hoyle predicted it would be at 7.65 MeV. Fowler's lab later confirmed the properties of the state, showing it could be formed from 3 helium nuclei and would decay into stable carbon-12. This was a remarkable achievement. Hoyle's prediction, born from the necessity of our own existence, was proven correct. William Fowler would later share the Nobel Prize in Physics in 1983 for his work on stellar nucleosynthesis. Fred Hoyle was controversially left out, but the coincidence does not stop there. The process needs a second fine-tuning. Once carbon-12 is formed, it could potentially fuse with another helium-4 nucleus to form oxygen-16. If this reaction were also resonant, all the carbon would be rapidly converted into oxygen, and again, there would be little carbon left in the universe. It turns out that the relevant energy level in oxygen-16 is just slightly below the combined energy of carbon-12 and helium-4. It is just out of reach. The reaction is not enhanced. This allows carbon and oxygen to be produced in roughly equal amounts inside stars. So we have a double coincidence. The energy levels in atomic nuclei, which are governed by the complex interplay of the strong and electromagnetic forces, just happen to be perfectly arranged. A resonance in carbon-12 is placed exactly right to allow its formation. A resonance in oxygen-16 is placed just out of the way to prevent its immediate consumption. If the carbon resonance were just 1% lower or higher, the amount of carbon produced in the universe would be negligible. If the oxygen resonance were just slightly higher, the same would be true. Without this delicate tuning of nuclear physics, carbon-based life would be impossible. The universe would be a place of only hydrogen, helium, and a bit of oxygen. Fred Hoyle himself, a staunch atheist, was so struck by this that he later wrote, "A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature." Whether one agrees with his conclusion or not, the Hoyle state in carbon-12 remains a stark example of a physical property that seems eerily fine-tuned for our existence. Number 11, water, the weirdest liquid. Water covers 71% of our planet's surface. It makes up about 60% of our bodies. Life on Earth is completely dependent on it. It seems so common, so normal. But from a chemical and physical standpoint, water is one of the strangest substances in the universe. Its properties are anomalous, and many of these anomalies are crucial for life. The most famous anomaly is its density. For almost every other substance, the solid form is denser than the liquid form. A block of solid iron will sink in a pool of molten iron, But with water, the solid form, ice is less dense than the liquid. Ice floats. Water reaches its maximum density at 4 degrees Celsius, not at its freezing point of 0 degrees Celsius. This happens because of the shape of the water molecule H2O and the hydrogen bonds between them. In liquid water, the molecules are jumbled together. As it cools, they slow down and pack closer, increasing the density. But below 4 degrees Celsius, the hydrogen bonds start to arrange the molecules into a rigid crystalline lattice structure. This open hexagonal structure takes up more space than the jumbled liquid state. So, as it freezes, it expands and becomes less dense. The consequences of this are profound. Because ice floats, it forms a layer on top of lakes and oceans in the winter. This layer of ice insulates the water below, preventing it from freezing solid. This allows fish and other aquatic life to survive the winter. If ice were denser than water, it would sink to the bottom. The lakes and oceans would freeze from the bottom up, eventually becoming solid blocks of ice, killing everything in them. The water also has an unusually high specific heat capacity. This means it can absorb a lot of heat without its own temperature rising very much. And it can lose a lot of heat without its temperature dropping much. The specific heat of water is 4,186 joules per kilogram per degree Celsius. For iron, it is only 450. This property is why coastal areas have more moderate climates than inland areas. The oceans act as giant heat reservoirs, absorbing heat in the summer and releasing it in the winter, stabilizing global temperatures. This thermal stability is also crucial inside living organisms, helping them maintain a constant internal body temperature. Water has a very high heat of vaporization. It takes a lot of energy to turn liquid water into water vapor steam. This is why sweating is such an effective cooling mechanism for many animals, including humans. As the sweat evaporates from our skin, it carries away a large amount of body heat. Water is also an excellent solvent, often called the universal solvent. Its polar molecules with a slight positive charge on the hydrogen side and a slight negative charge on the oxygen side are great at dissolving other polar substances like salts and sugars. This allows water to transport essential nutrients in the soil, in plants, and in the bloodstreams of animals. The chemical reactions that power life happen in a water-based solution inside our cells. Another crucial property is surface tension. Water molecules are strongly attracted to each other. At the surface, this creates a kind of skin. Water's surface tension is higher than that of almost any other liquid. This allows small insects to walk on water. More importantly, it is what allows water to be pulled up from the roots of a tall tree to its leaves, a process called capillary action. Each of these properties is unusual. The fact that one substance has all of them is a remarkable coincidence. The laws of chemistry and physics lead to this specific set of properties for H2O. And this specific set of properties seems to be exactly what is needed to create a stable environment for complex life to emerge and thrive. There are other liquids in the universe, like liquid methane on Saturn's moon Titan, but none of them have the versatile and life-supporting combination of properties that water does. Our planet is in the right place at the right temperature for this weird liquid to exist in abundance. Number 10, the sun's peculiar stability. Our sun is a star. There are hundreds of billions of stars in our galaxy alone. It seems like a typical average star. It is a G-type main sequence star, often called a yellow dwarf. But a closer look reveals that the sun is unusually stable and calm compared to most other stars of its type. This quiet nature may have been essential for the development of complex life on Earth. Most stars similar to the sun are much more variable. Their brightness can fluctuate significantly. They often produce powerful superflares, which are enormous bursts of energy and radiation, thousands of times more powerful than any solar flare ever recorded from our sun. A 2012 study of 83,000 sun-like stars observed by the Kepler Space Telescope found that many of them are far more active than our sun. Some of them produce superflares as often as once a century. If our sun were to produce a superflare of that magnitude, the consequences for Earth would be catastrophic. The initial burst of X-rays and ultraviolet radiation would severely damage our ozone layer, which protects us from harmful solar radiation. This would be followed by a storm of high-energy charged particles. This would cripple our power grids, destroy satellites, and pose a lethal radiation risk to astronauts and even passengers on high-altitude flights. The damage to the ozone layer would take years to recover, leading to increased rates of skin cancer and ecosystem damage. It is possible that a single superflare could cause a mass extinction event. Our sun does have a cycle of activity. It has an 11-year cycle of sunspots, solar flares, and coronal mass ejections. But even at its most active, it is relatively placid. The largest solar flare ever recorded was the Carrington event in 1859. It was powerful enough to set telegraph offices on fire and create auroras that were visible as far south as the Caribbean. But it was nowhere near the scale of a superflare seen on other stars. The reason for the sun's stability is not fully understood. It may be related to its rotation speed or its magnetic field, but the fact remains that we orbit a star that is an outlier in its calmness. The sun's stability extends over the long term as well. For life to evolve from simple microbes to complex organisms, it needs a long period of stable climate. The sun's energy output has been remarkably consistent over the past few billion years. It has gradually brightened as it has aged, which leads to its own puzzle, the faint young sun paradox, but it has not had the erratic wild swings in brightness that would have boiled or frozen a planet like Earth. The sun's position in the galaxy also contributes to this stability. It orbits the galactic center in a nearly perfect circle, in what is known as the galactic co-rotation radius. This means the sun stays out of the galaxy's dangerous spiral arms, where star formation is intense and nearby supernova explosions are more common. A supernova is the explosive death of a massive star. If one were to occur within about 30 light years of Earth, it could strip away our ozone layer and shower the planet with deadly radiation. By staying in a quiet, stable orbit in a calmer part of the galaxy, the sun has protected its planets from these cosmic hazards. So the star we orbit is not just a random G-type star. It is a star with an unusually stable light output, a lack of life-extinguishing superflares, and a safe circular orbit through the galaxy. These are not requirements for a star to exist, but they may be requirements for a star to host a planet with a 4 billion year uninterrupted history of life. Number 9, Jupiter, our guardian giant. Jupiter is the largest planet in our solar system. It is a gas giant with a mass 2.5 times that of all the other planets in the solar system combined. Its immense size and gravitational influence have had a profound effect on the history and structure of our solar system. For a long time, it has been thought that Jupiter acts as a cosmic shield, protecting the inner planets, including Earth, from frequent impacts by comets and asteroids. The early solar system was a chaotic and dangerous place. It was filled with trillions of leftover planetesimals, small bodies of rock and ice that were the building blocks of planets. For billions of years, these objects rained down on the newly formed planets in an era called the Late Heavy Bombardment. The moon's cratered surface is a record of this violent period. Jupiter's massive gravity would have played a key role in cleaning up this debris. It would have ejected many of these objects from the solar system entirely. It would have absorbed the impacts of many others. Computer simulations show that without a planet like Jupiter, the rate of asteroid and comet impacts on Earth would have been much higher, possibly as much as 1,000 times higher. One dramatic example of Jupiter's role as a shield was observed in 1994. A comet called Shoemaker-Levy 9 had been captured by Jupiter's gravity and broken into more than 20 pieces. Astronomers around the world watched as, one by one, these fragments slammed into Jupiter's atmosphere over several days. The largest impact left a dark scar in Jupiter's clouds that was larger than the entire planet Earth. If that comet had hit Earth instead, it would have been, an extinction event far greater than the one that wiped out, the dinosaurs. Jupiter continues to protect us. It deflects the paths of many long period comets that come in from the Oort cloud, the distant reservoir of icy bodies at the edge of the solar system. Its gravity can either fling them out of the solar system or change their orbits so they do not threaten the inner planets. However, the story is more complicated. More recent research suggests that Jupiter's role is not so simple. While it does protect us from long-period comets, its gravity may also be responsible for nudging some asteroids from the main asteroid belt between Mars and Jupiter into Earth, crossing orbits. So it may act as both a guardian and a threat. The overall effect is still debated, but many scientists believe the net effect is protective. The specific architecture of our solar system, with a giant planet like Jupiter in a stable, nearly circular orbit just outside the inner rocky planets, seems to be important. Some theories of planetary formation suggest that giant planets often migrate inwards towards their star, destroying or ejecting any smaller rocky planets in their path. These are called hot Jupiters, and they have been found in many other star systems. Our solar system seems to have avoided this. The Grand Tack hypothesis suggests that Jupiter did migrate inwards early in the solar system's history, perhaps as far as the orbit of Mars, but the gravitational influence of Saturn, the second largest planet, pulled it back out to its current position. This inward then outward journey would have scattered the material in the inner solar system, possibly limiting the size of Mars and delivering water-rich asteroids to the region where Earth was forming. So we have a series of coincidences. We have a massive gas giant, Jupiter. It is in the right place to protect the inner solar system. Its orbit is stable. It had a partner, Saturn, that may have prevented it from migrating inwards and destroying Earth. This specific arrangement of planets is not guaranteed. It is a particular outcome of the chaotic process of planet formation. But it is an arrangement that has created a relatively safe and stable environment for Earth over billions of years. Without our giant guardian, the history of life on Earth might have been a story of constant interruption by catastrophic impacts. Number 8, our precise location in the galaxy. Just as Earth's location in the solar system is crucial for life, our solar system's location in the Milky Way galaxy is also strangely convenient. Not all parts of a galaxy are suitable for life. There is a concept called the Galactic Habitable Zone GHZ, a specific region of the galaxy where conditions are most favorable. Our sun happens to be located right within it. The GHZ is defined by two main factors. First, you need to be in a region with enough heavy elements. Elements heavier than hydrogen and helium, which astronomers call metals, are created inside stars and spread throughout the galaxy by supernova explosions. These heavy elements are essential for forming rocky planets like Earth, and are the building blocks of life itself. The concentration of these elements is highest near the galactic center and decreases as you move outwards. So you need to be close enough to the center to have a good supply of these raw materials. But you cannot be too close. The center of the galaxy is a dangerous place. It hosts a supermassive black hole, Sagittarius A, which periodically flares up, emitting intense radiation. The density of stars is much higher there, meaning that gravitational perturbations from passing stars would be more common, potentially disrupting planetary orbits. The rate of supernovae is also much higher near the center. As we have seen, a nearby supernova would be devastating to life. There is also more high-energy radiation in general, so there is a sweet spot. You need to be far enough from the center to avoid the radiation and gravitational dangers, but close enough to have the necessary heavy elements. This ring-shaped region within the Milky Way is the Galactic Habitable Zone. Our solar system is located about 27,000 light-years from the galactic center, which places it comfortably within this zone. The coincidence is compounded by the sun's orbit. As mentioned before, the sun has an unusually circular orbit around the galactic center. Most stars have more elliptical orbits, which means they would pass through different regions of the galaxy. An elliptical orbit would take a star system in and out of the dangerous spiral arms. The spiral arms are regions of dense gas and dust where new stars are being born. They are sites of intense star formation and frequent supernovae. Our sun's orbit is special. It is at a distance called the co-rotation radius. At this distance, the orbital speed of the star almost perfectly matches the rotational speed of the spiral arm pattern itself. The result is that our solar system stays between the spiral arms for very long periods, hundreds of millions of years at a time. We are in a relatively safe, quiet neighborhood avoiding the galaxy's most violent events. So we are in the right part of the galaxy, the GHZ, and we have the right kind of orbit, a circular one that keeps us out of trouble. This has given Earth a very long period of relative cosmic calm, allowing billions of years for life to evolve without being repeatedly sterilized by gamma-ray bursts or nearby supernovae. Is this just a lucky accident? Maybe. Or perhaps it is another example of observational selection. We exist here, so our location must be one that allows for existence, but the number of just right conditions keeps adding up. The right star, the right planetary system, the right location in the galaxy, the right orbit in that location. Each factor narrows down the number of places where complex life could plausibly arise. Number 7, the proton-neutron mass difference. At the heart of every atom are protons and neutrons. Together, they are called nucleons. They make up almost all the visible matter in the universe. They are very similar in mass, but they are not identical. A neutron is slightly heavier than a proton. The difference is tiny, only about 0.14%. A neutron has a mass of 1.6749 x 10 raised to the power of 27 kg. A proton has a mass of 1.6726 x 10 raised to the power of 27 kg. This minuscule difference has enormous consequences. If it were even slightly different, the universe would be unrecognizable. Because a free neutron is heavier than a proton, it is unstable. A lone neutron will decay into a proton, an electron, and an antineutrino in a process called beta decay. The average lifetime of a free neutron is about 15 minutes. A proton, being the lighter of the two, is stable. As far as we know, protons do not decay. Their lifetime is estimated to be at least 10 raised to the power of 34 years, vastly longer than the current age of the universe. This stability of the proton and instability of the free neutron is fundamental to the structure of the universe. In the first few minutes after the Big Bang, the universe was a hot soup of protons and neutrons. As it cooled, they began to fuse together to form the first atomic nuclei. If neutrons were not unstable, they would not have decayed. This would have led to a very different mix of elements coming out of the Big Bang. But the real fine-tuning comes when we consider what would happen if the masses were different. Let's imagine a universe where the neutron was just a little bit heavier. If the mass difference were larger, neutrons would have decayed even more quickly in the early universe. Fewer of them would have been available to fuse with protons to form deuterium, the first step in creating helium. The universe would have ended up with almost pure hydrogen. Without helium, stars would burn very differently. The chain of nucleosynthesis that leads to carbon and other heavy elements would be broken. A universe of only hydrogen would be a much simpler and probably lifeless place. Now, let's imagine the opposite and more dramatic scenario. What if the neutron were slightly lighter than the proton? Even by a tiny fraction. In this universe, the proton would be the unstable particle. It would decay into a neutron, a positron, and a neutrino. Hydrogen atoms, which consist of a single proton and an electron, could not exist. The proton at the center would decay. If protons were unstable, the entire universe would be different. There would be no hydrogen, the most abundant element and the fuel for stars like our sun. The laws of chemistry as we know them would not exist, as they are based on the interactions of electrons with stable, positively charged nuclei. Atoms themselves would not be stable. The universe would be a neutron star-like place filled with neutrons and other exotic particles. There would be no stars, no planets, and no life. The actual mass difference, where the neutron is just 0.14% heavier, is in a tiny sliver of a range that allows for both stable protons and a long enough neutron lifetime for the right amount of helium to be synthesized in the Big Bang. This creates a universe rich in hydrogen, but with enough helium to get stellar processes started, leading to the creation of all the other elements. The masses of the proton and neutron are not arbitrary. They arise from the masses of their constituent particles, the up and down quarks, and the binding energy of the strong nuclear force that holds them together. So this fine-tuning of the neutron-proton mass difference is really a fine-tuning of the fundamental parameters of particle physics, like the quark masses and the strength of the strong force. A small change in these underlying constants would tip the balance, creating a universe where the building blocks of matter itself are unstable. The existence of a complex, chemically rich universe depends on this delicate and unexplained balance. Number 6, the strength of the strong nuclear force. There are 4 fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. The strong force is the most powerful of them all. It is what binds quarks together to form protons and neutrons. It is also what holds protons and neutrons together in the nucleus of an atom. Its strength is precisely tuned. If it were even slightly stronger or weaker, the universe would be sterile. Let's consider what would happen if the strong force were just 2% stronger. The effect on protons and neutrons would be significant. 2 protons could bind together directly, forming a diproton or helium-2. In our universe, the strong force is not quite strong enough to overcome the electrical repulsion between 2 positively charged protons. So, to form helium in the sun, a proton must first be converted into a neutron via the slow, weak nuclear force. This is the rate-limiting step in stellar fusion, and it is why stars like the sun burn their hydrogen fuel slowly and steadily over billions of years. In a universe with a slightly stronger strong force, diprotons would be stable. Hydrogen would fuse into helium almost instantaneously. The Big Bang would have converted all the hydrogen in the universe into helium and heavier elements. There would be no hydrogen left to fuel stars for the long term. There would be no water H2O. The universe would be a dark place with no long-lived, stable stars to support the evolution of life. Now, what if the strong force were about 5% weaker? The consequences would be just as dire. The force would be too weak to bind protons and neutrons together to form stable nuclei. For deuterium, a nucleus made of 1 proton and 1 neutron, would not be stable. Deuterium is the essential first step in the chain of nuclear reactions in stars. Without stable deuterium, stars could not ignite. The universe would be composed of only hydrogen. There would be no heavy elements, no planets, no life. Even if some heavier elements could form, a weaker strong force would make them less stable. The number of stable elements in the periodic table would be much smaller. The actual strength of the strong force lies in a very narrow window that allows for a universe with a rich and complex chemistry. And it is strong enough to bind a variety of stable nuclei, creating the periodic table. But it is weak enough that hydrogen, the simplest element, remains abundant and can fuel stars for billions of years at a slow, controlled rate. This fine-tuning is not just about the existence of elements, it is also connected to the Hoyle resonance for carbon production. The energy levels within a nucleus are determined by the strength of the strong force. The specific 7.65 MeV resonance in carbon-12 that is crucial for our existence is a direct consequence of the strength of the strong force being what it is. If the force were different, that energy level would be in a different place, and carbon production would fail. So the force that holds the universe's matter together is set at a value that seems just right. A small change in either direction would lead to a universe that is either all helium or all hydrogen, for a universe without the long-lived stars and diverse elements necessary for life. The reason for this precise value is one of the deepest mysteries in physics. It is a fundamental constant, but we have no theory that explains why it has the value it does. Number 5, why we have 3 dimensions. We live in a world with 3 spatial dimensions: length, width, and height. We can move up and down, left and right, forward and backward. This seems so fundamental that we rarely question it, but why 3? Why not 2 or 4 or 11? From a physics perspective, the number of spatial dimensions is a critical parameter of the universe. And it turns out that 3 is a very special number. Life, as we know it, would likely be impossible in a universe with any other number of spatial dimensions. Let's start with a 2-dimensional universe, a flatland. In 2D, complex life would face a fundamental problem with biology. A complex organism needs a digestive tract to consume food and excrete waste. In 2D, a tube passing through the organism from mouth to anus would cut the organism in 2. There is no way to have a sophisticated circulatory or nervous system that can connect every part of the body without crossing paths. The topology of 2 dimensions is simply too restrictive for complex networks. The physics is also problematic. In a 2D universe, the way waves propagate is different. It is more messy. A sharp signal, like a nerve impulse, would not travel cleanly. It would leave a lingering wake, causing confusion and echoes in any nervous system. What about a universe with more than 3 dimensions? Let's consider 4 spatial dimensions. Here, the problems are related to the stability of orbits. The force of gravity and electromagnetism follows an inverse square law in our 3D universe. The force is proportional to 1r raised to the power of 2, where r is the distance. This law leads to stable, closed orbits like the Earth's orbit around the Sun. In a universe with 4 spatial dimensions, the force of gravity would follow an inverse cube law 1r raised to the power of 3. In a universe with and spatial dimensions, it would be an inverse n1 law. It turns out that stable, closed orbits under a central force are only possible for an inverse square law. In 4D or higher, orbits are unstable. A planet would either spiral into its star or fly off into space. There would be no stable solar systems. The same problem applies to atoms. Electrons would either spiral into the nucleus or escape entirely. Stable atoms, the basis of all chemistry, could not exist. So 3D seems to be the only dimension that allows for both complex networks, unlike 2D, and stable orbits, unlike 4D and higher. It is a unique balance point. Some modern physics theories, like string theory, propose that there are actually more than 3 spatial dimensions. String theory requires 10 spatial dimensions to be mathematically consistent. To reconcile this with our observed 3D world, the theory suggests that the extra 7 dimensions are compactified. They are curled up into tiny subatomic circles, so small that we cannot perceive them or move in them. This leads to another coincidence. If there are extra dimensions, why did exactly 3 of them expand to become the large macroscopic dimensions we experience, while the others remain tiny? The physics of the Big Bang and cosmic inflation must be arranged in such a way as to produce this specific outcome. The dimensionality of our universe is one of its most basic properties. It is not something we can change, but when we examine the consequences of changing it, we find that our existence is tied to this specific number, 3. It is the Goldilocks dimension, not too simple, not too unstable, just right for complexity and stability. Number 4, the great attractor's pull. Our galaxy, the Milky Way, is not sitting still. It is hurtling through space at a tremendous speed, about 600 kilometers per second, 2.2 million km/h. But what is it moving relative to? It is moving relative to the cosmic microwave background, which acts as a rest frame for the universe. For a long time, astronomers assumed this motion was due to the gravitational pull of nearby galaxy clusters, like the Virgo cluster and the Hydra Centaurus supercluster. But when they mapped out the galaxies and their gravity, the numbers did not add up. There was still a large component of our motion that was unexplained. It seemed that our galaxy, along with its entire neighborhood of thousands of other galaxies, the Laniakea supercluster, was being pulled towards a specific point in the sky. This point lies in the direction of the constellations Centaurus and Norma. The object responsible for this pull was dubbed the Great Attractor in 1986. The problem was, when astronomers looked in that direction with their telescopes, they could not see anything massive enough to explain the pull. This region of the sky is obscured by the plane of our own Milky Way galaxy. The dense clouds of gas and dust in our galactic disk block the visible light from whatever lies beyond. This is called the zone of avoidance. The Great Attractor was a gravitational anomaly, a mystery hiding behind a curtain. Its mass was estimated to be enormous, equivalent to tens of thousands of Milky Way galaxies, concentrated in a region of space hundreds of millions of light years across. Over the years, using X-ray and radio telescopes that can peer through the dust, astronomers have been able to map this region more clearly. They found a massive supercluster of galaxies, the Norma Cluster, located right at the heart of the Great Attractor region. But even the Norma Cluster's mass did not seem to be enough to account for the entire gravitational pull. The story got even bigger. In the 2000s, further surveys revealed something even more massive lying even farther away behind the Great Attractor. This is the Shapley supercluster, a colossal concentration of galaxies about 650 million light-years away. It is the most massive structure in our local universe. It is now thought that the Great Attractor is not a single object, but the gravitational center of a vast overdensity of matter that includes the Norma Cluster, the Shapley supercluster, and other associated clusters. Our local group of galaxies is not just being pulled towards this region, it is flowing along with a huge river of galaxies, a bulk flow towards this massive concentration of matter. The coincidence here is not one of fine-tuning for life, but one of our specific place and motion in the cosmos. We are not just drifting randomly. We are part of a grand, coherent motion on an unimaginable scale. We live in a galaxy that is being pulled by the gravity of structures that are hundreds of millions of light years away. This motion has implications for our understanding of the universe. The existence of such massive structures and large-scale flows provides a test for our models of cosmology. According to the standard model, lambda CDM, structure in the universe grows hierarchically. Small clumps of dark matter merge to form bigger clumps, which then attract normal matter to form galaxies and clusters. The observed structures like Shapley and the bulk flow are on the very edge of what this model predicts. They are larger and the flows are faster than expected. The Great Attractor is a reminder that we are not isolated. We are part of a cosmic web of matter, connected by gravity to structures so large they defy easy comprehension. Our motion through the universe is dictated by the ghosts of matter we cannot easily see. It is a cosmic coincidence that our particular location in the universe places us on the slope of such a massive gravitational hill. Number 3. The KBC Void. For decades, we have used a specific type of supernova, type Ia, as a standard candle to measure distances in the universe. These supernovae are thought to explode with a consistent peak brightness, so by measuring how dim they appear, we can calculate how far away they are. It was by using these standard candles that astronomers in 1998 discovered that the expansion of the universe is accelerating, a discovery that led to the idea of dark energy. The calculations that led to dark energy rely on the cosmological principle. This is the assumption that on large scales the universe is homogeneous and isotropic. It looks roughly the same everywhere and in every direction. This means that our location is not special. We live in a typical part of the universe, but what if this assumption is wrong? A study published in 2013 by a team of scientists, Keenan, Barger, and Cowie, suggested that we might be in a very special place indeed. They proposed that the Milky Way galaxy is located near the center of a huge cosmic void, a region of space that is unusually empty, with a much lower density of galaxies, stars, and matter than the cosmic average. This void, now known as the KBC void, is the largest ever found. It is a sphere about 2 billion light years in diameter. It is not completely empty, but it is significantly underdense compared to the rest of the universe. If we are living in a giant void, it could have a major impact on our cosmological measurements. The gravitational pull inside a void is different from the pull in a denser region. The matter at the edges of the void would pull the galaxies inside it outwards, towards the denser walls of the void. This local outflow of galaxies would look, from our perspective, like an accelerated expansion. The idea is that at least part of the observed cosmic acceleration might not be a global phenomenon caused by a mysterious dark energy. It might be a local effect, an illusion caused by our position inside a giant bubble. The light from distant supernovae has to travel through the void to reach us. The changing gravitational potential as it travels could affect the light in a way that mimics acceleration. This is a controversial idea. Most cosmologists still believe that dark energy is real and the acceleration is global. The evidence for dark energy comes from multiple sources, not just supernovae. The cosmic microwave background and the large-scale distribution of galaxies also point to an accelerating universe. But the KBC void hypothesis has not been ruled out. It is possible that both effects are real. There is a global acceleration from dark energy, but it is being slightly distorted by our location in a local void. The coincidence is that we might be living in one of the emptiest places in the entire universe. If the KBC void is real, our cosmic address is not typical. It is exceptional. This would violate the cosmological principle, the bedrock assumption of modern cosmology. It also raises anthropic questions. Is there a reason why life might be more likely to arise in a void? Perhaps the lower density means fewer disruptive events like galaxy mergers or nearby supernovae providing a quieter environment. Or perhaps it is just a statistical fluke. The existence of the KBC void is still being debated and studied, but it presents a fascinating challenge. Our most profound discovery about the cosmos in recent decades, the accelerating universe, might be partly a result of a cosmic coincidence of our location. It forces us to question whether we are truly seeing the universe as it is, or if our view is colored by the unusual properties of our own cosmic neighborhood. Number 2, the CMB's axis of evil. The cosmic microwave background CMB is the most important source of information we have about the early universe. The standard cosmological model predicts that the tiny temperature fluctuations in the CMB should be random. There should be no preferred direction in the sky, no special patterns. The universe on the largest scale should be isotropic, the same in all directions. But when scientists analyzed the high-precision maps of the CMB from NASA's MAP satellite, and later confirmed by the European Space Agency's Planck satellite, they found something strange. There were several large-scale patterns or anomalies that did not seem to be random. The most prominent of these is a strange alignment of the largest patterns in the temperature fluctuations. When the CMB sky is broken down into a series of wave patterns like decomposing a musical sound into its constituent notes, the simplest and largest patterns are the dipole, quadrupole, and octopole. The dipole is mostly caused by our own motion through space, but the next two largest patterns, the quadrupole, a 2-lobed pattern, and the octopole, a 3-lobed pattern, are unexpectedly aligned with each other. They are also aligned with the ecliptic plane, the plane in which the Earth and other planets orbit the Sun. This alignment has been nicknamed the axis of evil because it threatens to undermine our standard model of cosmology. There is no reason why these large-scale patterns, which were imprinted on the universe when it was 380,000 years old, should have any relationship with the orientation of our solar system, which formed 9 billion years later. The alignment is statistically unlikely. The probability of it happening by chance is estimated to be less than 1 in 1,000. It suggests that there is a preferred direction in the universe, a cosmic axis, and that our solar system is somehow special with respect to it. Scientists have scrambled to find an explanation. Could it be a mistake in the data analysis? The WMAP and Planck teams have exhaustively checked their methods. The signal appears to be real. Could it be contamination from our own galaxy? The Milky Way emits microwave radiation that must be carefully subtracted from the CMB maps. But the axis does not align with the plane of our galaxy. It aligns with the plane of our solar system. This has led to some very speculative theories. Some have suggested that the universe is not isotropic on the largest scales. Maybe it has a non-trivial topology, like a donut, which could create such alignments. Others have proposed new physics, suggesting that the laws of nature themselves are not the same in all directions. Another possibility is that it is a fluke. In any random dataset, you can find seemingly unlikely patterns if you look hard enough. The 1 in 1,000 probability might sound small, but cosmologists look at thousands of different properties of the CMB. The chances of finding at least one strange thing are actually quite high. This is called the look elsewhere effect. Still, the alignment is deeply unsettling. It is a crack in the smooth facade of our standard cosmological model. It is a cosmic coincidence that connects the largest observable structure in the universe with the local arrangement of our own solar system. It could be a statistical fluke, it could be a sign of some undiscovered error, or it could be a hint that the universe is stranger and less random than we have assumed. Number 1, the faint young sun paradox. About 4 billion years ago, life on Earth was just getting started. The geological evidence from ancient rocks suggests that the Earth had liquid water on its surface. There were oceans, but there is a major problem with this picture. According to well-established models of stellar evolution, the sun was much fainter back then. It would have been only about 70% as bright as it is today. With a sun that dim, the Earth should have been a frozen wasteland. The average temperature should have been well below the freezing point of water. It should have been a snowball. Yet the evidence points to a warm, wet, early Earth. This contradiction is known as the faint young sun paradox. It was first pointed out by astronomers Carl Sagan and George Mullen in 1972. So what kept the early Earth warm? The most likely solution is that the Earth's atmosphere was very different. It must have had a much stronger greenhouse effect. The atmosphere likely contained much higher concentrations of greenhouse gases like carbon dioxide and methane. These gases would have trapped the sun's weaker heat and kept the surface warm enough for liquid water to exist. This solution makes sense. Early life forms like methanogens produced large amounts of methane. Volcanic activity was also much higher on the young Earth, releasing vast quantities of carbon dioxide into the atmosphere. So it is plausible that a super greenhouse effect was at work. But this solution introduces a new layer of coincidence. As the sun has gradually brightened over the past 4 billion years, the Earth's temperature has remained remarkably stable. It has had its ice ages and warm periods, but overall it has stayed within the narrow range required for liquid water and life. This implies that as the sun's output increased, the greenhouse effect of Earth's atmosphere must have decreased at a perfectly corresponding rate. It is as if the Earth has a global thermostat. As the solar furnace gets turned up, the planetary insulation gets turned down, keeping the temperature just right. What could this thermostat be? A leading hypothesis is a geological process called the carbonate silicate cycle. It works like this: carbon dioxide in the atmosphere dissolves in rainwater, forming a weak carbonic acid. This acid rain falls on silicate rocks, weathering them. The weathered minerals, including calcium and bicarbonate ions, wash into the oceans. In the oceans, marine organisms use these to build their shells of calcium carbonate. When they die, their shells sink to the ocean floor, forming limestone rock. This process locks atmospheric carbon dioxide away in stone, reducing the greenhouse effect. This cycle has a built-in feedback mechanism. If the Earth gets warmer, rainfall and weathering increase, pulling more CO2 out of the atmosphere and cooling the planet down. If the Earth gets colder, weathering slows down, allowing CO2 from volcanoes to build up in the atmosphere, warming the planet up. This geological thermostat seems to be the answer, but it is a slow process operating over millions of years, and it relies on a complex interplay of geology, biology, and chemistry. It requires active plate tectonics to recycle the crust and fuel volcanism. It requires the presence of liquid water. It requires the evolution of life that uses carbon to build shells. The faint young sun paradox points to a remarkable 4 billion year balancing act. The sun's luminosity has changed dramatically. The Earth's atmosphere has changed dramatically. Life on Earth has changed the atmosphere. Yet through it all, the planet's climate has remained hospitable. The Earth's geological and biological systems seem to have worked in concert to perfectly counteract the changing output of our star. It is a long-term coincidence of stability that has allowed life to persist and evolve from the simplest microbe to the complex ecosystems we see today. The fact that the Earth has this self-regulating system and that it has worked so well for so long is one of the most profound just right conditions for our existence.